So in several of the videos so far, we've talked about the necessity of considering more than one equilibrium in the solution. In other words, this class is really introducing you to the notion that we can't really think about one reaction at a time. There's almost always going to be a series of reactions, whether that is additional complexation reactions, which we talked about with lead and iodide, right? If you add more and more ligand, like an anion like iodide, to a heavy metal like lead, you can actually go beyond the point of neutrality, beyond PbI2, and make lead I3 minus and resolubilize lead in that case, in which case we have to consider all of those things. Not to mention, if we have acid-base equilibria, virtually all anions can also interact with protons, right? For that example, if we're thinking about I minus or iodide, you can have HI, right? So the pH of the solution also is going to be a large function of the HI equilibrium. So there's lots of equilibrium going on simultaneously inside of a beaker, especially for natural waters or drinking water, things like that. But we don't yet have a methodology by which we can approach that complexity simultaneously. That's what this component of the chapter is. And so if we have got lots of equilibria and we want a method by which we can sort of proceed from simplicity to complexity, that's what systematic treatment of equilibria is. And that's what the name implies, right? It's a systematic approach to solving the complex equilibrium system. In less abstract terms, what it really means is writing a system of equations, mostly in the form of equilibrium expressions, such that the number of equations that we have is equal to or greater than the number of unknown variables. We can solve that system of equations using a variety of techniques. In this class, we'll use just substitutional algebra. But of course, if you had taken linear algebra, matrix algebra, that's the proper way to solve these, and that's how software programs will solve them. So we'll use software that employ matrix algebra, but no linear algebra required for this class, just giving you a sense for how you would do this efficiently. So you essentially, regarding the system of equations, you're essentially going to write out all equilibria. So write out all equilibrium expressions. So that means you need to know the k's for each of those values, so the equilibrium for all the species that you know. And then we're going to need to add to that, we will see that that's not going to be enough to satisfy the notion that we need at least the number of equations as unknowns to solve them. We're also going to have to introduce these two new types of expressions. They're not that challenging, but there was probably no reason why you would have needed to know them before. And those are going to be called the mass balance and charge balance equations. And typically they're for any set of for any chemical system, there's going to be one charge balance where you essentially write an expression that relates all the concentrations of the anions equal to all the concentrations of the cations. And that has to be true, right? Because all solutions are neutral. And so that's going to be our charge balance equation. The mass balance equation, there are often several, and it's a little bit more nuanced. And so we'll start with the charge balance, and then we'll talk about the mass balance. But the goal here is just to generate all the equations we can and then simultaneously solve them. So charge balance is the simplest, and as I mentioned, this comes from the conservation of charge and the fact that you have to have the same number of positive and negative charges in a solution to preserve what's called electroneutrality. And so the sum of all the positive charges have to equal the sum of all the negative charges. What that looks like in practice is you can write up an expression of concentrations where you will have the charge on the ion, Z, times the concentration of that thing, C. All of those have to equal the charge on, we'll say, the cations, and that'll be an A for the anions. So we're going to use the charge to multiply, as a coefficient, multiply the concentration. And that makes sense, right? Because if you have something like iron 3, its contribution to the overall charge balance is going to be 3 times that of something like a proton, which only has +1. So I've got an example here. We'll write this out really quick. So how do we write a charge balance for a system like this? And this may look complicated, but this is a fairly normal solution if you really consider. Actually, there's not much going on here. You've got water, you've got a little methanol, you've got probably an ammonium buffer, and then you've got a perchlorate salt, and some potassium ferricyanide. And so this is a standard electrochemical cell. And so there's a lot going on here. The first thing to do when you're looking at this, if it's a charge balance, anything that's neutral is not going to contribute. So we can go through, we can say water's not going to do anything, the methanol is not going to do anything, and the ammonia is not going to do anything. Everything else looks charged. So then we'll just go through and set up a condition that looks like this. So let's just do positives on the left. We'll start with protons here. Let's do this in green. So we've got the concentration of protons, and I'm just going to cross things out as I go, plus 3 times the concentration of iron, plus 2 times the concentration of magnesium, 2 plus, again, these are just coming from the charge values, plus the ammonium ion concentration, and that looks pretty good to me. So I'm going to set that equal to the hydroxide ion concentration, which is plus the perchlorate concentration, plus cyanide concentration, plus chloride concentration, and then plus this ferricyanide complex. 3 minus, and that's going to be in parentheses, and I'm going to multiply that by 3. Okay, so this is it. This is your charge balance equation, and all this tells you is that all of the concentrations of these ions, modified by whatever their charge is, all of that charge, all that positive charge here has to, or the concentration of that positive charge has to equal the concentration of this negative charge based on the conservation of charge or electroneutrality rules. So what's the purpose of this? Well, it just presents to us another algebraic expression. That's going to be useful if we're trying to do substitutional solutions of simultaneous equations, right? If you've got a whole bunch of systems of equations, right, all of these concentrations of species, they're all unknowns, right? We don't know any of them. And so we will have to generate a series of equilibrium expressions for each one of these based on what sort of reactions they're participating in, plus a charge balance equation, plus as many mass balance equations as we can get to, such that we have a series of equations where we have at least enough, or at least as many as all of these unknowns that we have here. We're not going to do this because this is going to take forever. We'll do a simpler example, but first we're going to jump into mass balance just so that we have that cleared up, and then we'll do an example of systematic treatment. So charge balance used the notion of electroneutrality to equate a new algebraic expression that we could then put into our system of equations to just give us a little bit more wiggle room for solutions. Mass balance is similar, but instead of electroneutrality as the principle that we use to generate the new algebraic expression, we're going to use the conservation of matter. And for that reason, there's usually several different ways, not usually, sometimes there are several different ways by which we can employ conservation of matter even in the same system. And that's why there is often multiple mass balance equations where there are only ever one charge balance equation. So as an example, I'm going to give you 2 different types of mass balance scenarios that you might encounter. One would be where you have known amounts or concentrations of stuff in solution, and you can use those numbers to generate a mass balance. The alternative is that you actually aren't given known quantities of anything, but you can implicitly, based on stoichiometry, generate a mass balance relative to ions in solution, typically based on the dissolution of an ion compound. So for this example, you know the formal concentrations of several of these species. So by formal concentration, I mean the concentration of the stuff that you put into the solution pre-equilibrium. We know that here we've got 0.0250 K2PO4, so this is a potassium sulfate or phosphate salt mixing with a strong base KOH in 1 liter. And 1 liter just makes it convenient because these are essentially concentrations then. We know that when you mix the K2PO4 with strong base, it's going to react, right? But without having to compute the equilibria, which is really the goal, and we can't compute the equilibria because there's going to be other things in the system. So we can't just simply say, okay, well, what's left over after these 2 react? But we can write a mass balance. So we can negate whatever the equilibrium is, but we can still compute a generic relationship for what is present in solution. So what do we do? So what remains unchanged in the solution? In other words, what's a spectator ion in this reaction? Well, you can look at certainly the potassium here and the potassium here are not going to change, right? This is an acid-base reaction. The potassium ions are essentially just carrying those conjugate acids and bases to the solution. So neither of those things are going to react, which means that we could write a mass balance equation simply for potassium ion. Right? So potassium ion, what does the concentration of potassium have to be in solution? Regardless of what equilibria take place, we know that it's not going to be destroyed in any case because it's fully soluble in all these compounds. So the concentration of that is going to be equal to the 0.30 mole plus 0.0250 mole, all in this case divided by that 1.0 liters. So that's going to give us a concentration here, if I computed it, to 0.0550 molar or moles per liter. So this expression here doesn't look like much of an expression, but it is, right? It's like saying x is equal to 2. Now we have one variable equal to a constant value. That's really helpful when trying to solve a system of equations. So this is one example of a mass balance equation from this example. We can also generate another one here. So let's think about this species, this phosphate species. So we can write an expression that says that the phosphate here, it has to, all the versions of phosphate, right? We're adding 0.0250 moles. We know that the KOH is going to react and probably generate a variety of different phosphate species here. Knowing that the acid-base system for phosphate is coming from phosphoric acid, right? So phosphoric acid, if I just sort of write this out, can lose a proton to make H2PO4 minus, which can lose another proton, which makes PO4 2 minus, which can lose the final proton to make PO4 3 minus of the phosphate ion. So that's the phosphoric acid system. We don't know exactly the concentrations of any of the individual phosphate species, but we do know that this is the only source of the phosphate into the system. And if we're adding exactly 0.0250 moles of it, then what has to be true is that all of those species, all those phosphate species together collectively still have to add up to 0.025. They can change species by adding and removing protons via this system, by the acid-base system, phosphoric acid, but collectively you can't destroy any one of those things. So that means the phosphate ion plus the HPO4 2 minus ion plus the H2PO4 minus ion plus H3PO4, all of those species together, which make up the entire phosphoric acid system, still have to equal 0.0250 moles per liter. And so this is another expression. It's now 4 different unknowns set equal to a constant. And so now from this example, we generated 2 mass balance expressions. We could go through and generate a charge balance, which means we'd have 3 new expressions in addition to all of the equilibrium expressions that we're going to generate relative to all of the acid-base reactions, essentially each one of these. And all together, if we can get to a point where we have enough equations that satisfy at least the same number of unknowns, then technically we can solve it. It's not going to be pleasant, but we can solve it substitution. Okay, the second scenario in which you may be asked to write a mass balance equation, or which you probably will be asked to write a mass balance equation, would be when you're not given an explicit concentration. So in this case, we're told that we have a saturated solution of silver phosphate. How can we use simply the stoichiometric relationship between silver and phosphate in this ionic compound to generate a relationship, a mass balance relationship? In other words, how can we relate the concentration of silver ions to the concentration of phosphate ions, simply knowing that when you have a saturated solution of a solid, what that really means is that solid is going to dissociate via some KSP, equilibrium. So in this case, that presents 3 silver ions plus a phosphate 3 minus ion. So you can think about this a couple different ways. As this silver phosphate ionic compound dissolves, it creates 3 silver ions for every 1 phosphate ion. So at equilibrium, for this saturated solution, the way that you can think about this is that the silver ion concentration is going to be 3 times the concentration of phosphate because of this 3, right? Because we're producing 3 of those for every 1 of the phosphate. So 3 of these for every 1 of those. So if we think about just the silver, then the silver ion concentration is growing 3 times as fast. So every 1 silver phosphate formula unit dissolves, we get 3 times silver and only 1 times phosphate. So that means the concentration of silver in solution is going to be 3 times that of phosphate, which you would write out as silver equal 3 times phosphate. This, make sure you understand what this is saying, right? Because this is the opposite of what's written in the actual equilibrium expression, where we have 3 silvers and 1 phosphate. Because when you say this out loud, it's actually the opposite of the way it's written in the reaction. So if we produce 3 silver ions for every 1 phosphate, that means silver concentration is going to be 3 times greater than the phosphate. So this would be a valid mass balance equation in this case. The other way to think about this is if we thought about this as an ice table, which you don't have to, but if it's helpful to you, you can think about that the starting concentration would be 0, 0, 0, and the change here would be minus x, some amount of x is silver phosphate. For every 1 of those x's, we're going to get 3 x's here, and we're going to get 1 x here. And so in that case, the silver is 3 times more concentrated than the phosphate. How do you write that algebraically? Silver is equal to 3 times the concentration of phosphate. And so the mass balance expression in this format, in this example, where you're not given an explicit concentration, it can be a little bit tricky to wield. And so you want to stop the video and really make sure you understand what's going on here and how you would write this expression. If we go back to our lead phosphate example, which we'll talk about quite a bit in this class, we could write a mass balance for this as well, right? And similarly, these coefficients get swapped when we're talking about the concentrations, when we're thinking about it from the perspective of the other. So this would be 2 times lead concentration equal 3 times phosphate concentration. So if I were to solve for lead concentration itself is going to be 3/2 the concentration of phosphate. Or in other words, lead 2 plus concentration at saturation of lead phosphate is going to be 1.5 times the phosphate concentration. And that makes sense, right? Because lead, for every 1 of these lead phosphates that dissolves, we get 3 of these and 2 of these. And so the concentration is moving up at a rate that's 50% faster than that of phosphate, meaning the concentration is going to be 50% higher, 1.5 times the concentration.